Greetings, welcome back to Randomtronic. My name is Chris and today I received a package in the mail. OWON VDS1022i PC oscilloscope. This is a 2-channel 25 MHz USB oscilloscope from OWON. In the VDS series, this is the smallest model, I guess. Also has got the lowest sampling rate of 100 mega samples per second. However, I think this will be perfectly sufficient for what I want to use it for. So here in the box we have the oscilloscope itself. Nice compact unit, ultra thin. It's an isolated USB on the back of the oscilloscope. Isolated BNCs on the front of it, channel 1, 2 and multi. We also get a bag with some literature, a CD with software and a bag of Bnc test probes and a USB power cable. This is the VDS1022i. It's a 25 MHz, 100 meg samples per second. I can see there are 2 screws on the back right under the rubber ends and 2 more screws like that on the front. So let's get a Phillips screwdriver. A self-tapping screw, I can kind of feel it, and yeah, I think it goes straight into aluminium extrusion. Okay, the back comes off. Here that this channel is meant to accept a self-tapping screw. There's nothing wrong with that. Okay, and there we go. Let's have a look at the parts. Analog front end canal, which I'm not going to remove. There's only some passive components, presumably. There's a trim pot here and here for channel 1 and 2, some compensation / adjustment. Here and here we've got identical channel paths. Let's focus maybe on one. So we've got AD603AR, and this is a 100 MHz op-amp. Yeah, this amplifies the signal coming out of analog front end, and that goes into LMH6551MA, which is another op-amp. It's a differential op-amp driving the differential pair that goes into this chip over here, and it's exactly the same arrangement, and a differential pair coming out into this chip. And this part, MXT2088, is a dual 100 MHz A to D converter. So this is what gets the differential inputs and converts them to ones and zeros that can be modified later on with Xilinx Spartan FPGA. It's a Spartan 3 FPGA, XC3S200A. There's a tiny little STM32U156 Cortex M3 microcontroller, and the USB is here, and as we can see it's an isolated USB. So we've got the DCP0205 and 05 is the voltage. This is a isolated DC to DC converter, so as you can see there is a massive gap in here, and this is the input and output of the voltage. Here we have analog devices, ADUM3160. It's a special chip for isolating USB connectors. So all as described in the listing so far. There are a few unpopulated components on the board. The interesting bit is differential op-amp is not 100 MHz. This model is 25 MHz, so no problem there. However, the same oscilloscope comes in a 100 MHz variant, and I'm wondering whether they use different chip, because that would have to be at least of 100 MHz bandwidth for the other ones to be 100 MHz. Bandwidth of this, I believe, is 90 MHz. Power generation for the FPGA and the processor, that I think is a shift register. 74HC595 would be a shift register. Not sure the purpose of that over here. Some switching perhaps, controlled by the microcontroller. SGM8272, it appears to be a dual op-amp, high voltage rail-to-rail op-amp. There are a few bodges in here. Resistors right next to it, 164. See, this one has been added on as an afterthought, and this one here at the very end. Some inductors, so I think there's some more power happening over here. We've got inductors and large capacitors. Some other models of this have also got a network LAN port. This is where the port would be, so I think the other models have got a different board altogether. And we have a nice little plastic pouch with the Bnc probes. Probes feel a little bit plasticky, to be honest. Yeah, a little bit of a plastic feel. The little hooks are a little bit rough. Probe is yeah, not sharp at all. Could be better. This comes off, and again this is, as you can see, a little bit on the rough side. 1x, 10x 300, 600 volts cut 2 with a compensation adjustment. P2060 voltage probe. Okay, and here we are. That's connected. We've got a rather big screen from a little oscilloscope. Let's put some signal into this and see what will it show. So I've got the FY3200S signal generator here. Channel 1 we want to switch off for the time being, yeah. And I think Control Enter should do auto setting for the waveform. Oh, there we go. There's a little bit of ghosting happening on channel 2. This is just a 50 Hz signal. It's showing 50.00 Hz. Let's see what happens if we connect the test signal on the oscilloscope. There we go. Let's maybe do both of them at the same time and we can compensate the probes properly. I can hear some switching happening in here. I didn't see any relays on the board. Could have been under the can. 1 kHz square wave, 2 volts per division. So we can adjust trigger. It's a little bit tricky this way, but we can always use the mouse. This is supposed to be a 25 MHz oscilloscope, so let's see how the signal looks if we feed it 25 MHz signal. So I'm just going to switch off the channel 2. And go to channel 1, coupling AC probe times 10. Yes, that's correct. It's on times 10. Oh, that's interesting. So we can select show all and shows all the measurements for what's on channel 1. It's having slight trouble triggering over here because I think the volts per division is slightly small. Or we can do XY mode. We'll try that in a moment. Peak detect mode, average. Okay, I'm feeding it 10 volts right now at 10 kHz. Okay, this interface works quite nice with a touch screen. Yeah, I can definitely hear relays clicking inside. What's going on there? It's not very happy there. I think after the auto set it goes funny when there's nothing connected to it, so increase the frequency a little bit. We've got 100 kHz and we're feeding square. Let's give it, there we go, a nice sine wave. Okay, that's 300 kHz. Okay, we're at 50. Let's go to 5 microseconds. There we go. Pretty. Let's do 1 microsecond. Okay, we can increase 400. That's a megahertz. 2, 3, 4. So far so good. We're at 4 megahertz. 100 nanoseconds. Okay, 10 megahertz, and it's still showing what resembles a sine wave. That's 24, and that's as far as my signal generator is going to go. Tops out at 24 megahertz, but at 24 megahertz you can see that the wave is starting to become a little bit jittery, and yeah, I think we're reaching the limit clearly. Still recognizable as a sine wave, so no problem there. Only the amplitude has dropped quite a bit, feeding it 10 volts, and we are at 5 volts per division. So right now, maybe let's change the scale slightly. So 5 volts, let's do 1 volt. Yeah, there we go. So we're full scale now, 10 megahertz, and you can see it starts dropping 19 megahertz, and we are showing already that's 8 volts, not 10. 23, 24, at 24 megahertz. This is 6 volts peak to peak, not 10 volts. That's, I guess, to be expected. It's about 15 megahertz. It's quite close, really close to what it should be. So now we can maybe look at different waveforms out of the signal generator. Here's a square of the same frequency, so it's a 1 megahertz at 10 volt peak to peak. That's a pulse, and it doesn't like triggering on this, so we need to raise the trigger a little bit. There we go. On triangle, no problem. Sawtooth, reverse sawtooth, rectified sine wave. This is pre-2. It's probably a noise, either white or pink noise, not sure. Another type of noise. Preset 4, preset 5, that's trapezoidal. Preset 6, I think this is the heartbeat electrocardiogram AM signal, and it's finding it slightly difficult to trigger, so we can hit F5 to start and stop to stop the waveform. It's a shame it doesn't do zoom like this. Yeah, interesting this, so let's zoom in a little bit to that. Oh, that could be FM modulation. Yes, it is. It was just a little bit too high on the frequency range. You can clearly see the frequency being changed, and yeah, that's the FM frequency modulation. I've connected both channels right now to two separate channels on the function generator. Let's put it into the XY mode, which was somewhere, there we go, channel 1 and channel 2. Okay, let's close that and see what happens. Both channels are at 100 kilohertz. And yeah, there you go. We get the Lissajous figures. Channel 1 at 200, 300, 400. And we can play with the trigger and that will rotate the figure. That's quite cool. Why is there nothing being displayed in the little quadrant here? It's taken the whole display, the width-wise, to display the waveforms, and then 1/4 of the display is being used to display the Lissajous figure, the XY mode, and this one shows nothing. So I'm wondering, is it just going to stay blank or not sure? But hey, this works and I'm quite happy with this. It's a really good bit of kit. OWON VDS 1022i 2-channel USB oscilloscope, 25 MHz. Works well with a touchscreen. I like the software. Yeah, I hope you enjoyed this video. This will be coming up a lot more often. We'll play with different oscilloscope measurements. But for today it's getting late, so thank you very much for watching, and please do subscribe for more random electronics related stuff. For today that's it. Take care, and my laptop's switched off.